You're welcome to synthesis of primary amine, the Gabriel synthesis. Amines as a class of organic compound derived from ammonia, where one of the three hydrogen atoms are replaced by alkyl groups. They are also known as functional groups that contains basic nitrogen atom with a lone pair. Amines are classified as primary, secondary, or tertiary depending on the number of hydrogen atoms replaced. Amines have many uses, including the production of medicine, drugs, azo dyes, nylon, and personal care products. The synthesis and primary amines, the Gabriel synthesis. The mechanism of reactions. Electrons flow from this region, from left to right, then back to right. So it is a chemical reaction that will be referring to this mechanism. This chart will be referring to it more often. Our rubric demands that acid workup ionization. This is sodium hydroxide here, and this is how it's ionized. In its electron form here, this has 2 pair of electrons. Is willing to have it has 4 pair of electrons and will be accepting 6 pair of electrons. It will be accepting 2 more. It's in need of 2 more, and so it's in its nucleophilic state. Here is water and there is hydrogen, and they will ionize this way. Potassium hydroxide ionizes this way too. The problem of multiple alkylations that we will see at the end of the exercise. Step 1, electron flow, nitrogen and potassium here. The negative charge nitrogen electron pair is nucleophilic. It attacks bromide at the alpha position, and bromide is a leaving group. As a consequence of that attack, it leaves. Here is what I mean. Here is nitrogen here, negatively charged, and potassium positively charged. The pair of electrons of the nitrogen will attack bromide. This is bromide here, attached to a butyl. So, as a consequence of this pair of electrons attacking bromide from the alpha position, bromide is cleaved off. It leaves. It's a leaving group as a consequence. And nitrogen replaces it. And not only does nitrogen do that, it carries the whole molecules and bonds at this point, forming an approximate octet configuration with a butyl group. As a consequence, an imide is formed. Step 2. In the presence of a potassium hydroxide base, a substitution reaction occurs, leading to the formation of 2 more hydroxy groups attaching to the amide, thereby forming the carboxybutyl amide, a bigger compound and a poor nucleophile. In the presence of alkyl halide and hydrolysis, the reaction undergoes a carboxylation, cleaving off the hydroxy group to form a primary amine out of a single alkylation. This is what is meant. Here, nitrogen has moved, as it has displaced. A substitution reaction, SN2 reaction, has taken place, and here, nitrogen has migrated to form part of the amide, taking along the butylamide. So this bond here, under a halide alkylation, comes to form an amide inside here. That is a sodium hydroxide, what that was mentioned, that led to carboxylation and alkylation to cleave off these 2 hydrogen here to form an amine. So single alkylation will give you a fine amine here. No secondary or tertiary amine attached. And so further alkylation would not occur. The steric effect. The reason the single alkylation reaction produced only one amine is the steric effect of after production of an amine. The resultant molecule stereochemical orientation in space has become too large by the bulking group, carbonyl group, to accommodate a further alkylations. Notice that the nitrogen here has become saturated. The nitrogen here has become saturated as a result of this bond here. So nitrogen has no affinity again for further alkylation. As a consequence, here, nitrogen has no appetite for further alkylations. As a consequence, the reaction will not go further. Rather, it will stay pure amine here at this production. This is the 2-hydroxy group I once referred to you that were cleaved up as a consequence of carboxylation, hydrolysis. This cleaved up, and this product was formed as a consequence. Here, amine was formed. And so, in summary, mechanism of reaction of amine requires this nitrogen here to cleave at this position of butyl bromide. Bromide is a living group. It moves off. It cleaves off. As a consequence, it is substituted by the nitrogen here into this position, and then moves on to bind with the amide compound here. You can see this here. In the process of alkylation, carboxylation, hydrolysis, all of that, the excess carboxy groups, hydroxy group that is formed as a consequence, are cleaved off to produce a fine amine. Notice that this is a primary alkylation that produced this amine, clean, no secondary amine or tertiary amine attached. Then the further attempt to alkylate this product will not go further because the nitrogen group here has no appetite. It's not nucleophilic, has no appetite for further alkylations. Therefore, this reaction will not go further. And the question becomes why? We say it cannot go further because this nitrogen atom or in the body of the amide is less nucleophilic. It has no appetite for further alkylation because it's already in its octet state. So, and the molecule has become so large. So the consequence of that is its orientation in space will limit further alkylation because nitrogen has no appetite for attaching other alkylations. So secondary alkylation is rejected. As a consequence, the reaction stopped. Thank you very much for listening.